Thanks everyone for coming today to today's AC-File seminar. Today's speaker is Patricia Pauli. So Patricia is a PhD student from the University of Stuttgart. She is doing a PhD there. She holds master's degrees in mechanical engineering and computational engineering, and her research interests are in robust machine learning and learning-based control. Take it away.
Thank you very much, Phil, and thank you for coming today. My name is Patricia Pauli. I've been at the AC-File for a little over 2 months now, and I'll be here for another 3 weeks to visit as a part of my PhD that I'm doing under the supervision of Professor Frank Algover at the University of Stuttgart with the Institute for Systems Theory and Automatic Control. Today, I would like to talk about some of my research I've been doing throughout my PhD. And the title of today's talk is Robustness Certification and Training of Robust Neural Networks using Lipschitz-bounded. Neural networks are ubiquitous. They are successfully applied in many fields, for example, in classification tasks like the classification of digits from 0 to 9, or also in segmentation tasks where objects are being told apart in pictures. Also in reinforcement learning, where an agent interacts with the environment, oftentimes their policy is parameterized by a neural network. So they appear everywhere. They're very successful and really popular these days. But also there are still some problems with neural networks. And one problem I'd like to look into is that neural networks are susceptible to adversarial attacks. What does that mean? Well, it's easiest to see that on an example, as we can see in this slide, where we have a picture that you would usually get in autonomous driving. It's a picture of a street where there are pedestrians in the picture, and a neural network was trained to do segmentation on that picture. And usually the neural network would recognize that there are pedestrians in the street. But now what is done if you create an adversarial attack, some noise is added to the picture that doesn't alter the picture much. It looks very much the same if you look at the bottom, but the segmentation is completely different. We cannot see the pedestrians in the street anymore, and the neural network has been fooled. And as you can imagine, this is especially dangerous in safety critical applications, such as autonomous driving. And we want to look into this issue of robustness and safety of neural networks using the toolbox from control theory. Control engineers are experts in properties like robustness, stability. We know a lot about guarantees. It's a well-established field. And why not use these tools now to say something about neural networks? So what we want to do is that we want to propose an analysis and training of robust neural networks using tools from control theory. And with that, we get to the outline of today's talk. First, I gave a short motivation. Next, I'd like to talk about the term robustness, what it means, and then we start with the main part of the talk that is split into 2 parts, starting off with fully connected neural networks, where we will look into Lipschitz certification thereof, and then into training of Lipschitz-bounded fully connected neural networks. Second, we will look into convolutional neural networks together, and there also at Lipschitz certification of 1D convolutional neural networks. So let's start with robustness. Before I said we want robustness against adversarial attacks, but how do we actually measure robustness? We can use the Lipschitz constant as a robustness measure. Lipschitz continuity is a sensitivity measure to changes in the input. Also, as we can now see in this box, if a function is Lipschitz continuous, if there exists some else such that this inequality holds, meaning that if there's a small change in the input and also the Lipschitz constant is small, we have a good bound on the change in the output. Also, if we look at the small animations up there with a smooth function, the change in the input between 2 axes does not cause such a big change or jump in the output. The cone that is characterized by the Lipschitz constant isn't so large, whereas in a noisy function and a pointy function, a change in x can cause quite a jump in the output, and the cone is larger here. So what you are supposed to get from this slide is that a low Lipschitz constant of a neural network means that this neural network has high robustness. This is how we want to think about it. And with that definition now, or this notion, we can look into fully connected neural networks. And first up, we will see Lipschitz certification of fully connected neural networks. That means we have a neural network given that was trained beforehand, and we want to now find a good bound on the Lipschitz constant of this given neural network. What is a fully connected neural network? Just so we are all on the same page, we have a bunch, well, we have an input layer and an output layer, and a bunch of hidden layers that hold nonlinear activation functions phi. The layers are all connected by linear layers that are characterized by weights and bias terms. And the description mathematically is shown down below. And this picture is something you often see with neural networks. So this is what we mean if we talk about fully connected neural networks. And we've seen that the Lipschitz constant is a good robustness measure. And there's the problem that the neural network is nonlinear, has all these nonlinear activation functions, can be quite large and deep. And this structure is quite hard to analyze, or it's quite hard to determine this Lipschitz constant, this exact true Lipschitz constant. What we can do though is we can find a description of the neural network that allows us to determine Lipschitz bounds. So we will only find an upper bound, but we will at least be able to find something. And to do that, we exploit that the activation functions that are commonly used in neural networks are slope restricted. On this slide, we see two examples of common activation functions, which is the rectified linear unit and the tanh function. We can see that the slope is restricted by the values 0 and 1. And this is slope restriction, or also, as you can see in the box, this is the way you can write it. This holds for every single neuron we have in the neural network. And based on this notion, we can now over-approximate the nonlinear activation functions, and that makes it amenable to a Lipschitz analysis. How does this actually work though? How can we now certify a Lipschitz bound for the neural network using a matrix inequality? So we're given a fully connected feed-forward neural network with L hidden layers, and we have slope restricted activation functions. Now, if we suppose there exists some L squared and some multiplier lambda, lambda is just a diagonal matrix that gives us some degrees of freedom here, that a matrix inequality holds, then the neural network is L Lipschitz continuous. So the L we see will be our Lipschitz bound we're looking for. The theta that M depends on holds all the weights and the bias terms, all the parameters of the neural network. Lambda is, as I mentioned, just some multiplier. And yeah, for now, it's just important that we have a matrix inequality constraint, which is a sufficient condition for Lipschitz continuity of the neural network. What it looks like is something we will look into later. So this is our certificate, but what we actually want is a Lipschitz bound that is really close to the exact bound, or as close as we can get with our over-approximation. And this is something we can find solving a semi-definite program that is now stated on the slide on the bottom. We minimize this L squared subject to the matrix inequality constraint. And this was how we can do certification, but it might also be interesting at times to already define before training that a neural network is supposed to be robust by giving a Lipschitz bound, by deciding that we want a Lipschitz bound for the neural network that we are training before training, and only restricted training to Lipschitz bounded fully connected neural networks. How do we go about this? In training of neural networks, you usually have a learning objective, and we still have that as well. That can be the mean squared error, the cross entropy loss, depending on the task we want the neural network to learn. And we also include the matrix inequality constraint from the previous slide. So we end up with a constraint optimization problem that you can now see on this slide. That's nice, but it's also can be quite a large matrix, and we don't really know yet how to solve it. And what is quite important about solving this optimization problem now is that we have good scalability of the training to deep neural networks, and we want to look into the details how we can really achieve that. How do we do that? A constraint optimization problem is never nice. So instead, we formulate an unconstrained training objective, including a barrier term, such that it looks like this. If we do so, we can use gradient descent optimizers and do training. But I went over this barrier term quite quickly. Actually, I want to talk a little more about it. The barrier term is this log. That function is quite commonly used for this kind of positive definite matrix constraint. And what it does, I called it barrier term. It sets up a barrier, as you can now see in the picture here. The barrier term actually approximates the indicator function. The indicator function is infinity, where the matrix inequality constraint is infeasible, and 0, where it is feasible. And now we have this nice approximation. If we now play around with the factor rho, we can also play around with how good the approximation of the indicator function is. And that is actually something that is adjusted during training. We will start having a large value of rho and then go smaller to get closer to the actual indicator function throughout training. So yeah, this is our barrier function. But what are other challenges that we have in our particular problem? We need positive definiteness of this matrix M we've seen before. And we need to make sure that at all times during training, we have positive definiteness. So we have to start off with an initialization that renders the matrix inequality feasible. That is actually something that is quite easily done for this kind of problem. We can just choose the initial weight entries quite small. If you think about it, if the weight entries are a 0, then the Lipschitz constant will be 0. And it's a continuous function. If we go a little bit higher than 0, we still have a small Lipschitz constant. So initialization is not a problem. Now, if we also want to have feasibility after an update step, that is a little trickier, and we have to discuss this a little more. I'll leave it at that for now. And another challenge is the efficient computation of the gradient, which we will need using gradient descent optimizers. The derivative of J is quite easy to find. It's standard in neural network training, and we obtain it via backpropagation. And then there's this other term with the log that function, and that is a little bit tricky because it contains finding an inverse, and finding an inverse of a very large matrix can be expensive. So how do we go about it? I now show you, as promised, what this matrix M actually looks like. If we look at it, we can see now that L, we can see the multipliers lambda, and the weights W naught to WL. They all appear. But what else can we see now that we look at this matrix? We can see that it has a particular structure. It has a block tridiagonal structure. So we have a block here, a block there, block there. They all are on the diagonal. And yeah, what's the problem? Well, we want to find the inverse of this. And what is oftentimes done if you want to find an inverse of a matrix, you find the Cholesky decomposition thereof. This is also something we want to do, where we find some L. L is now a triangular matrix. And we don't only, without thinking, find a Cholesky decomposition, but we do it blockwise. We can exploit this structure with all this sparsity on the sides and perform a blockwise Cholesky decomposition, which is computationally favorable. With that, we have found a way to efficiently compute the inverse in this way. So that was one of the problems mentioned on the previous slide. Also, what's a quite nice property of the Cholesky decomposition is that it exists only if the matrix is positive definite. And this is something else we wanted to do. So to check positive definiteness of the matrix M after an update step, well, if we can do the Cholesky decomposition, we're good and know that we have positive definiteness. So we get that for free because we needed it for the derivative anyway. With that, the two problems we've seen before are solved by the blockwise Cholesky decomposition, or let's say at least we go a little more smartly about it than if you just put it into a solver. And now we've looked at the details of this training theme. And next, I'd like to show some examples where we applied this training scheme to show that it actually works. Here we use a fully connected neural network with 2 hidden layers, cross entropy loss. We choose the robustness level, the Lipschitz bound, to be 20 and have activation functions ton h. We train a neural network to classify the digits from 0 to 9 on the NNs data set. And we did that for a nominal neural network, meaning we have no constraint, and for a Lipschitz neural network using our method. And what we can see here in the results is that the Lipschitz constant of the nominal neural network is really high. It's almost 600. That indicates to us it's not robust. The test accuracy is quite good. And the Lipschitz neural network, however, also has a good test accuracy. And Lipschitz bound after training that is below 20 as is expected. There's some conservatism. That's why it's only like at 70. Also, what was important and why we did all the tricks on the previous slide is that we have scalable training, and we can see on this example, it takes only 1.7 times longer to train our Lipschitz neural network, which makes our method applicable to this size problem. And yeah, we've seen it works. The Lipschitz bound is small, but is it actually more robust against adversarial attacks? That is something we want to look into next. And for that, we generated adversarial examples using the fast gradient sign method. Here in this picture, we are comparing for different perturbation strengths. There are a nominal neural network and an L2 regularized neural network and Lipschitz neural network, and compare on adversarial attacks how good the accuracy is. And what we can see, well, the L2 regularized neural network also is more robust than the nominal neural network, but at the no perturbation, it has as you can see, you can't really see it on screen, but here, does this work? Yeah, as you can see here, it has a worse accuracy in the nominal case without perturbations. It is definitely more robust, as you can see that for higher perturbation strengths, the accuracy stays up, but the Lipschitz neural network really does better than both of the neural networks we compare it to. And also, I'd like to show some pictures here with different perturbations. Here we have a perturbation that changes the number 1. We cannot really see that the picture is different, and both neural networks at this perturbation strength are still able to classify the number correctly. Now, with this perturbation strength, the picture does change a little bit, but with the human eye, we can still see that this is a number 2 and not a number 3, but the nominal neural network was actually fooled. And now with even larger perturbations, it gets also hard for us to see if this is now a 9 or 4, and also the neural networks are both now fooled. But what we can see from this slide is that Lipschitz neural networks really show an improved robustness against adversarial attacks. Also, I would like to show you some other example where Lipschitz constraints can be useful. And for that, I want to introduce, or show you what generative adversarial networks can do. What can they do? They can generate pictures that look very much like real people. The people in the picture look like real people. For example, this person does not exist in real life, neither does that one or that one. And this person is me. But can you really see the difference and see who is real and who isn't? And that's what they can do. They're quite cool and powerful. But what are they made up of? They consist of 2 neural networks, a discriminator and a generator, that have different jobs. The discriminator is trained to distinguish data in a data set from artificially generated data, and the generator is trained to generate an output that is as indistinguishable as possible from the data in D. The training problem for GANs looks like this. We have a min-max optimization problem training both neural networks at the same time, but the title has something that says Wasserstein. Actually, this training problem had some problems to it. It was not really stable and robust. That's why it was modified and resulted to be the Wasserstein GAN training. The difference is that a Lipschitz constraint was added to one of the neural networks, to the discriminator. So now this training problem restricts the discriminator neural networks to be one Lipschitz continuous. And here we have our Lipschitz constraint that we can include into training using a matrix inequality like we've seen before. And that is what we did. And we compared that to other state-of-the-art methods in Wasserstein-GAN training. And here you can see the results. We used the same architecture and trained for the same number of epochs. We can see that the fake images using our method look really close to real numbers, whereas the other two methods struggle after 100 epochs to produce pictures that look like real numbers. If we next compare the computation time, we can see that weight clipping and gradient penalty are quite similar, and we take 2.4 times longer for this kind of training, but we also need less epochs, so that's fine. And what's also quite nice, what we can see here is that we've had a really large structure, including convolutional networks, and our training method was applicable here. And with that, we get to the end of this part of the talk. We saw that a Lipschitz constant is a good robustness measure. We saw that nonlinear activation functions are slope restricted, and we saw linear matrix inequality. That was a sufficient condition for Lipschitz continuity. And from that, we were able to propose a method that trains robust neural networks, meaning that we actually have guarantees on the Lipschitz constant for the neural network after training. Also, we saw that this method is scalable with the tricks we applied to deep neural networks, for example, neural networks that are used in Wasserstein-GANs. The results that I presented in this part of the talk are written up in these two papers. The second one is a paper that I will be presenting at CDC this year. With that, we get to the second part of this talk, and I'd like to talk about convolutional neural networks next. What we do here now is Lipschitz certification again. That means that we are given a convolutional neural network and want to find a Lipschitz bound for this given convolutional neural network, and especially for 1D convolutional neural networks. And why would that be interesting? Well, many state-of-the-art neural networks include convolutional layers and pooling layers, so it should be something that is considered. Convolutional layers are quite cool. They are characterized by just a small filter that captures the dependencies between pixels that are just next to each other and then make up the convolved image like you can see in this animation, and average pooling is used for downsampling. But yeah, we want to look in these kinds of elements. And with the methods we've seen so far, what can we do to do Lipschitz certification? The convolutional layers can be written as feed-forward layers. That's what we did in the previous part of the talk. But actually, this formulation is highly redundant and very sparse and has bad scalability to deep neural networks. We must be able to do better there. Also, the pooling layers can be nonlinear, and for example, maximum pooling is. And so far with the methods we've seen, we cannot include nonlinear pooling layers. And in this part of the talk, we suggest a layer-wise dissipativity-based approach for Lipschitz certification of convolutional neural networks. We restrict ourselves to 1D convolutional neural networks. That means we don't have a picture input, but like a time series, as you can see here, that only propagates in one direction. Also, here I've shown all the components that we can see in the convolutional neural networks that we are considering here, which are convolutions. We have nonlinear activation functions, we have the pooling functions, and usually you would also see some fully connected layers in a convolutional neural network, and the flattening operation between the convolution and the pooling layers and the fully connected layers. All of these components can appear several times. Just for ease of exposition, they only are shown once here. And what we want to do, I mentioned the word dissipativity. We want to make sure that every layer, every component is QSR dissipative. So this part is QSR dissipative, this part is QSR dissipative, this one and this one as well. What is this dissipativity? Well, we'll define it later, but for now, just think of it of some property that these individual layers have. And once we've set up these properties and make sure that they are ensured, then we can connect the input and the output through the dissipativity properties of the individual layers. In the end, we want to know if the input to the output map is Lipschitz continuous, and we can do that through this connection and through dissipativity. And right, let's look at the different parts of the convolutional neural network, starting with the convolution that gives it the name. A convolution can be written like this, characterized by a convolution kernel. There's a bias term. There also is a nonlinear activation function again, but this description doesn't get us so far. And as control engineers, we can also see this as a finite impulse response filter. And also, if it's written like that, it's also causal, and we can find a discrete time state space representation thereof that looks like this. So we find the matrices A, B, C, and D, where C and D hold the parameters of the kernel, and A and B have this structure. With this description, very compact, we can now look into dissipativities for this kind of CNN layer. We call a CNN layer QSR dissipative if any input-output pair satisfies this property here, characterized by Q, S, and R. So it has what we also say, it has a positive supply rate. So this is the property we want to have. And how do we make sure that it has this property? We can do that, again, by a linear matrix inequality constraint. If this linear matrix inequality constraint down here holds, we make sure that it holds, then we know that the convolutional layer is QSR dissipative. So with that, we get to the fully connected layers, and we'll look into dissipativity for these as well. Their definition of dissipativity is very similar. That's now we again have a supply rate now for fully connected layers. And again, we can make sure that we have dissipativity by enforcing some LMI constraint. So if this LMI holds that we see down here, then the fully connected layer is actually QSR dissipative. Next up, let's look at the nonlinear activation functions once again. We've seen before that these are slope restricted, and we've seen this picture before. But what I want to point out now is that we can formulate an incremental quadratic constraint, like we can see in this lemma, to describe the slope restriction of all neurons in the neural network. So, well, we have this activation function, and we have here the multiplier. Lambda also appears, and this is the incremental quadratic constraint that over approximates all the activation functions in the neural network. And I showed you this because we want to do something similar for the pooling layers. Pooling layers are used for downsampling. They can be nonlinear. It's not so easy to include them in our state space description. And that is why instead we want to find incremental quadratic constraints for the pooling layers. For example, for average pooling, what does average pooling mean? Well, we get a vector input, take the average of all the vector values, and then that's the output. It's applied channel-wise. Just for completeness, here we have actually, well, it has multiple channels, and it's a signal with multiple time steps. We can choose two different partitions. Here we need the partitions of using the row vectors, but now formulating an incremental quadratic constraint, we need a different partition. That's just for completeness, but it really has the same entries. And what I want to show here is that we can now formulate an incremental quadratic constraint that looks like this. For every average pooling operation, this property is fulfilled for all positive definite matrices T. So that's quite nice and follows the concept of activation functions. Now we also have maximum pooling. That is also an operation on a vector. It takes the maximum of this vector, and we can also formulate an incremental quadratic constraint that now looks like this for all sigma that are diagonal matrices with positive entries. Okay, But we've talked about dissipativity before, and now about incremental quadratic constraints. And what we want to do now is put them together. The pooling layers are incrementally QSR dissipative as well, as we can see if we choose a parameterization where we choose Q to be minus sigma, S to be 0, and R to be this. And this is just a special case with a special parameterization of QSR dissipativity. But they also are, so we can include them in our framework. And with that, we now have all the ingredients for all of the components to put it together. As I mentioned in the beginning, we want to make sure that every layer is QSR dissipative, using LMIs that we even force, or using incremental quadratic constraints. So this will be QSR dissipative, this will be, and as well will this one. Next, now we have properties of all the individual layers, all the subsystems. And we connect them, well, we connect the input and the output through the interconnection, through the dissipativity properties of the individual layers. How do we do that? Using an LMI again. Let's look at the details. We make sure all layers are QSR dissipative, meaning that they fulfill this property. We can do that by LMIs. The additional LMI looks like that. It holds now all the Q, S, and R of all the layers that are connected in this LMI. Why it looks this way isn't so important, but it implies an inequality that looks like this. Now, we know that all the supply rates are positive, and we can use this information to get rid of them in the inequality, which then implies this condition. And this condition is Lipschitz continuity from the input of the first layer to the output of the last layer. So this was a way how we used dissipativity to get a property from input to output. And this is how dissipativity is usually used. You know something about subsystems, about the individual layers, but want to know something about a complex overall structure and make the connection using these dissipativity properties and knowing how they are interconnected. And we summarize this in a theorem that looks a little bit large, but what it basically says is that we want to make sure that, well, we have a CNN given, we have a gamma given, which is the Lipschitz bound, and all activation functions are slope restricted. Now we want to make sure that LMI holds for all CNN layers. We want to make sure that LMI2 holds for all FC layers, fully connected layers. So both of them are dissipative through these LMIs. We use a parameterization for all the pooling layers, like shown before, and we have the connection through LMI3. And if all these LMIs hold at the same time, then the CNN is gamma Lipschitz continuous. Again, this is just the LMI test. Now, if we want to find an upper bound that is really close to the actual true Lipschitz constant, we will solve a semi-definite program again. As you can see, we minimize gamma before, have a bunch of decision variables, and we have now 3 LMI constraints, or well, for all the layers, we have the constraints, but multiple LMI constraints. So this is how we want to do the test, and this is something we applied on some toy examples. Here we have a fully convolutional neural network that has, well, 3 CNN layers only. You see here the kernel on the channel sizes. We generated the weights randomly. And now for rising input dimensions, we did our Lipschitz certification test. And what you can see, and then we also compare it to other methods from the literature. LipSDP is something that we've seen in the beginning of the talk, so it relies on writing the convolutional layers as fully connected layers, and we applied a theorem and a method from the beginning of the talk. Triv is a trivial bound that is just the product of the spectral norms of the weights. What we can see in the pictures is that the trivial bound is very conservative, it's much larger. The LipSDP neuron and the LipSDP layer are quite good for very small input dimensions, but as we get larger, they are really comparable to our method as well. And also we see that our method is independent of the input dimension. That becomes favorable, especially if we now look at the computation time, where we see that the computation time rises drastically for higher input dimensions for libSTP, and it's independent for our method, which is quite nice if we have high resolution signal inputs. Next, I'd like to show another example of deep convolutional neural networks. Here we have this structure that we see here with some convolutions, some pooling layers, more convolutions, an average pooling layer, and also a fully connected layer. What we did now was, for this structure, we generated randomly 10 sets of kernels and weights and biases. So we generated randomly 10 instances of neural networks and analyzed the Lipschitz bounds for all 10 of them. And what you can see in the picture is that the trivial bound is, for all of the instances, much larger than both of the bounds, the comparison bound libSTP and our bound that we call dissipativity. The blue and the red bar are quite similar, but you can see the difference when you look at the average time of them, how long their certification really took. And we can see that our method takes only 3 seconds, whereas libSTP took 750 seconds. And 150 is not even a large input signal. If we go larger with the input dimension, libSTP will run into memory errors easily, and we cannot apply the method at all anymore. Whereas our method is independent of the input dimension. The trivial bound is still faster, but it really isn't that good. So we are more accurate with our method and have a really good Lipschitz bound. With that, I come to the end of this part of the talk. We've seen dissipativity for all the individual layers of the convolutional neural network. We've seen a compact description of convolutional layers in state space, which was handy to use. We've established incremental quadratic constraints for pooling layers. With these ingredients from the control toolbox, we were able to propose a method that determines an accurate Lipschitz bound for 1D convolutional neural networks, and it is scalable to deep convolutional neural networks, and especially with high resolution, as it is independent of the input dimension. What else? What's next? So the next steps include the Lipschitz analysis of more general convolutional neural networks that include 2-dimensional CNNs, and also something that we've seen in the first part of the talk was the training of Lipschitz-bounded fully connected neural networks. And what would be interesting would be training of Lipschitz-bounded convolutional neural networks. With that, I would like to thank a bunch of people, some of the PhD students from my group that are Anne Koch, Julian Berelis, and Dennis Kramlis, also some students that I've worked with and that have contributed to some of the results here, that are Paul Kohler, Niklas Funke, Armin Usmaimi, and David Gekela, my PhD supervisor, and the funding agency Deutsche Forschungsgemeinschaft. I want to thank you for your attention. I look forward to your questions. And yeah, that's it.
Thank you. Great talk. We have time for questions now. So if you have a question, put your hand up online as well.
Yeah, thanks, Patricia. Excellent presentation, very clear. With the comparison between the convolutional approach and the libSTP kind of, that's just assumed like treating them as fully connected networks and using the previous work, right? If you on the previous slide where you're looking at input dimension, I noticed that for smaller inputs, the libSTP approach does do better. Do you know what is, so why are they not equivalent? Why do you think there's some kind of conservatism introduced in this convolutional representation, which only seems to show up as small inputs, but it's there nonetheless?
Yeah, exactly. Well, first of all, small inputs, well, you will never have a time series that is as an input dimension of 10, so they're not really relevant. But what is actually true is that our method will always be worse than libSTP neuron. We can show as we go to infinity with libSTP neuron, so in the input dimension n equals infinity, then they will, their method will converge to ours. Yeah, ours from the start is well, works for all input dimensions, and that includes infinity, and that's why we have this gap there for smaller dimensions than infinity. But yeah, yeah.
What's the source of the gap? Is it in so you're doing a kind of layer-wise QSR certification, and then those combine into a kind of full network certification. Do you think is the conservatism relative to libSTP, is it in the individual layer certifications, or is it in the kind of approach of doing a layer-wise decomposition and then combining them with a QSR?
So I think about that question. Where does the conservatism come from? Well, a few things that are interesting in that respect is that we can choose this. We've chosen a state space representation. I'll go back to that so everyone knows what I'm talking about. So we've chosen a state space representation of the convolutional layers, and we've chosen a minimal one. We can choose a different one, and that will also change our Lipschitz bound. If we don't choose a minimal one, we can have a better Lipschitz bound. That is, which I find quite interesting, actually. Where that really comes from is, I mean, the stage becomes larger, and we carry that information in the storage functions that are also included in their dissipativity approach. So there is kind of more information in it, but that is something that apparently is one source of conservatism here. Well, so that's where the conservatism comes from in the, one source of conservatism in the dynamical systems, in the convolutional layers. If we only had fully connected layers and connected them through dissipativity, then we can show equivalence of the dissipativity approach and the approach we've seen in the beginning, connecting them by, if the matrices Q are chosen as full matrices.
So using kind of the big block LMI is equivalent to having QSR.
Exactly. Yeah, that is interesting. Well,
so if you're training with this method, which I know is kind of the next steps,
yeah,
you could also train over similarity transforms of this state space representation,
right?
Certify those, right? And that might reduce the conservatism.
Yeah, it could be interesting to look into that. Yes.
Okay, great.
Yeah. Thank you.
Thanks. So I had a question from Patricia online.
It's not a question, just that so at some point you were inverting tridiagonal matrix.
Yes.
I think if it's a symmetric matrix, there's a cross-ball. To do that, but it's more efficient than the Cholesky.
All right. Yeah, that's the one we want to invert.
Yeah, it's
Okay.
Matrix. So there is a close form for that. It's symmetric.
It is symmetric.
Okay.
Okay.
So that's cheap. More efficient because Cholesky is calculated some order. But I'm not necessary. I think even use Wikipedia to formula to calculate that.
All right, I'll look into it. Thank you for making me aware of that. Yeah, it's probably might still be very useful to do it blockwise, which
fast, but you don't need that. So I can get it fast.
All right, good. Yeah, thank you very much. Yeah, I feel like we should still do it blockwise because this way we exploit the sparsity, but yeah, if we can do that blockwise part more faster, that'd be interesting. Definitely.
All right, any other questions?
I've got a question on the learning perspective. So the talk started with a robustness to adversarial attacks.
Right.
So the methodology applicable to not only adversarial attacks, but basically all sorts of comprises.
Right.
Okay.
So, well, yeah, we use the Lipschitz constant. So we just checked it on adversarial attacks because that's one of the biggest problems. Those attacks are really generated in a way that they, generate the worst case noise. But all kind of noise, we also see this better improved robustness on Gaussian noise, on uniform noise. Yeah, definitely.
It's just because the visual data are complicated, we can't issue the underlying distributions. Otherwise, you might be able to design some specified methods to cater to those special assumptions to data distributions. That will be even more applicable to real applications with this issue.
Okay. Yeah, we've never gone towards real world applications. Yeah, I'm not sure if I was able to follow everything you just said.
Okay, that's fine.
I don't know if this is exactly what you're suggesting, but one possible thing that can be done and has been done in kind of like stability analysis uses of IQCs is you don't necessarily just have to look at Lipschitz constant or L2 gain and so on. If you have some way of characterizing likely disturbances with an IQC type representation, then you can do a bound with respect to those kind of likely disturbance structure. And so this, if it's like a sub-Gaussian distribution or something, this is because Lipschitz bound or L2 gain, it's worst case, right? But you might know that there's a certain likely kind of spectral structure of the disturbances. If you can write that as an IQC, then it's easy to incorporate into this. You just have it on the left-hand side instead of the identity.
Right, yeah, that makes sense. Yeah, that's nice about the framework in general and dissipativity, that you're quite flexible with the properties you want to verify.
Yeah, so I know your work is a lot about like mathematical robustness, but if you're looking at, so you're going off the intuition and applying of the Lipschitz continuity, it has a smooth response to disturbances. And if machine learning is already a big computational, can you just do a numerical method for that? And then you do a backpocket step, and then you run a few forward steps and disturbances, and then you look at the disturbance and the distributions of that and see, and from there you can use that to very cost and additional cost as well. And with that
right. I feel like there are a lot of other approaches to go towards this problem of adversarial robustness. One example is that definitely that you generate a lot of adversarial data, for example, and use them as additional training data that will also improve the robustness. You can probably play around with it and make some combinations of these methods. Yeah.
Because I'm just going off that intuition point and see how does a numerical method like that stack up to actual robustness like this?
Definitely, it might be in applications that might be even work better. We come from a theoretical side and really look at guarantees. Yeah.
So I'm trying to get my head around you showed as an example the classification of numbers. But I mean, a classification problem on its output is inherently not continuous. So how does it work with being Lipschitz bounded Lipschitz continuous if the output is actually a categorical thing, which is discontinuous?
Right. So the way we think about it is that the output is a vector of, you will have a vector that has 10 entries. And all of these entries correspond to one of the classes, 0 to 9. And after that, we apply a softmax function to that. And then the most likely class will be identified, which has the highest probability in that vector. All the entries add up to 1, and the highest one will give us the class. And we look at the vector before the softmax layer, actually. So that vector is actually continuous. And there you have a continuous transition from one number to the other. So what I find actually quite interesting is if you look at here, that we also see that there is a continuous transition between the number 9 and the number 4. If we make these adversarial attacks, and that's something you can see in this vector. Does that make sense?
Yeah. Okay.
Yeah, well, yeah, it's so, well, what at some point you will have an entry 0.4 for the number 4 and an entry 0.4 for the number 9, and that's the transition point. And yeah, and well, once it goes, you go a little more towards number 4, it will go up, and then we'll identify it as a 4. That's the output we see. That's if we have discrete outputs, it's number 4 or number 9, but the vector and the output we actually work with in this problem is the vector that has the probabilities.
Do you see a way of somehow certifying the, like, one step further, like the actual discrete output in some way?
And that, well, there is, let's see. For me, that's how far we need to go. And Lipschitz continuity is only a good measure if we have the smooth functions, or otherwise can't really work with it.
There is some work, I'm not super familiar with it, but some work relating if you've got Lipschitz bounds before the softmax and then a categorical, like decision boundaries formed by the softmax, then I think you can relate the Lipschitz bound to something like a margin, like as you would have in an SVM. We've got kind of the maximum margin classifier, kind of distance between, maximizing the distance from the decision boundary to the training examples. I vaguely remember reading something about that somewhere, but I can't put my finger on exactly what it is.
Yeah, this has a good follow-up on that. Even if you do it before the softmax layer, that function is still going to be continuous, but still change drastically at the decision boundaries. So how does that work with Lipschitz?
It will not change that drastically if the Lipschitz constant is low. So that's.
What, according to data, you do need it to change drastically.
Then the Lipschitz constant is probably not the right robustness measure.
Does anyone else have any questions?
Right.
Yeah. I have a question about the scalability. Could you please go back to the block Trotsky declaration slide? Yes. So you have block Trotsky declaration is very efficient if L is sparse, but L inverse could be a density matrix. Also, is a no triangle. And when you're using like automatic differential, basically you need to trace one of the variable, intermediate variable. Then I have a question about the scalability of this approach. So yeah, L is sparse, but
right.
L inverse could be dense.
L inverse could be dense, yeah. Right?
And you need to compute the like a gradient of this matrix, right?
Yeah. So what there are some details to it you can consider. We don't only have the inverse of the matrix M, but the derivative also has some matrix multiplication that retrieves the sparse structure that we have here. So what we can do, or what we also do, is that when we find the inverse, we don't find all the entries of the inverse, but only that the entries of the inverse that will not be zeroed out by the sparsity pattern that we have up here to save some of the computational effort. Right. And also we do this blockwise to, cut down the computational effort as much as we can. But yeah, you could also do, you would want to get rid of the constraint in general and choose a direct parameterization to get rid of constraint, which is even nicer.
Any last questions?
Let's say your methods try to minimize the Lipschitz constant, and you basically will find what's the word that I was wondering if we have a small Lipschitz constant that it influences the generalization of the network. Some trade-off between
so what I've been reading a lot is that there is a correlation between generalization and robustness. That's also quite interesting. One way to look into generalization, or if you want better generalization, you often use a regularizer like L2 regularization, like we do here. And here we can see that this L2 regularization also improves the robustness. So there's a correlation, but where we actually have a trade-off is between accuracy and robustness, or accuracy and generalization, that we see in L2 neural networks. The accuracy became worse, but the generalization became better. Here, and well, with our method, we were a little more, using the Lipschitz constant is a little more direct in the sense of directly going for the Lipschitz constant, and also worked a little better than the robustness while still containing a good accuracy.
All right, thank you. Any other question? All right. Thank you very much, Patricia.
Thank you.